Assalamualaikum and hello. Alright, so today I would like to discuss on lecture 7, which is the linear momentum and moment of momentum equations, as promised. So these are the contents of this lecture, the derivation of momentum equation and some of the examples of the application of momentum equation, and last but not least, the moment of momentum equation. So as introduction, motion of fluid is dependent of Newton's second law. So what does Newton's second law of motion state? It states that the rate of change of momentum of a system in the direction of the force is equal to the net external force on the system in the same direction. Okay. So in Newton's second law of motion, okay, Newton's second law of motion, it states that F is equal to ma. Okay, the net force. Okay, the net force, the net external force acting on a system is equal to the rate of change of the momentum. So m can also be written as A can also be written as dv over dt. Okay, so if you combine m into this, you should get dmv over dt. So m times v is basically momentum. Okay, m times v is basically momentum. Okay. So dmt over dt of the system. Okay? Force acting on the system. Alright. Okay. So for fluid, since the control volume approach is used, or control volume approach is another name of Reynolds transport equation. Okay? General control volume equation is another name of Reynolds transport equation, which I have derived in the lecture, in lecture 6 previously. Okay. So remember that when I derive the Reynolds transport equation, which can be used as a tool for analyzing the fluid motion, okay, I use X, X which denotes the any extensive properties. Okay, then I change the X. Okay, so this is the general Reynolds transport equation. Then I change X previously with M, mass. Then I get the mass conservation equation. Okay. So now, in this lecture, I will replace this X with momentum. Okay. So since momentum has direction, so for example, I show the example for momentum in X direction, mx. Okay. So I replace X with momentum in X direction. So this is the rate of momentum of the control volume in the X direction. This is the rate of momentum of the system in the X direction, plus summation of rate of momentum in X direction at the inlet minus outlet. Okay, and then by the Newton's second law of motion that I have just shown just now, the net external force acting on the system is equal to the rate of momentum of the system. Okay, the rate of momentum of the system in the same direction. So you can replace this term with the summation of force or external force acting on the system. Okay? So when you replace, you should get this equation. Okay, so this is the general force and momentum equation, or also called as linear momentum equation. Okay, and this one is the equation for the non-uniform flow, where you need to do the integration, where the dA is the area of the or the differential area of the pipe. Okay, and if you still remember, if the flow is steady, so this term of the rate of the excessive property of the control volume. So in this case, is the rate of momentum of the control volume should be 0. Okay, for a steady flow, the rate of momentum of the control volume should be 0. So when you make that 0, so you rearrange the equation, you will get summation of force in the x direction, since this is x direction, is equal to summation of rate of momentum of the at the outlet in the x direction minus inlet. Okay, and this is the equation for non-uniform flow, where you have the integration here with respect to the area. Okay, so note that these equations can be applied to y and z direction as well, but separately. Okay. Okay, there's some notes on the applicability. The net force and net of all external forces acting on the control volume. So there are two types of force. So there are two types of force. One is the boundary force, such as pressure force, which acts normal to the surface and towards the control volume. Okay. And another one is the shear force, which acts parallel to the surface and parallel to the control volume. Okay. And the second one is the forces across the control volume boundary. For example, the gravitational force, which is the weight, or the magnetic force. But most of the time, the magnetic force is ignored. Okay, we don't consider it, and we don't know what's the value, okay, unless it's given. Okay, the same with the shear force. If it's not given, then you just assume 0 lah. Basically, if the forces cannot be found, cannot be calculated, or not given, then we can just ignore the forces lah. Okay. Alright, the application of force and momentum equation or linear momentum equation to the control volume is analogous to drawing the free body diagram in solid mechanics. So meaning, before you answer the question, you have to draw the free body diagram so that you know what are the forces acting on the body. Okay? Okay. So to answer the example, the question of force and momentum equation, there are a few steps that you need to follow. Okay. Okay. Let's say in this example we have a vein. Okay. So what's a vein? A vein is a blade. We can call it a blade lah. Okay. A very thin, a flat plate lah. Okay. So in this diagram, we have a vein. So fluid flows on the vein. Okay. The vein is open lah. Okay. So the fluid flows on the vein. Okay. To find the horizontal and vertical component of the force exerted on the vein. Okay. So the force exerted on the vein. So before that, the first step that you need to follow is, the first one is to choose a suitable control volume. Okay. Let me draw this. Okay. Sorry. Okay. I just draw here lah. Okay. So this is the vein. So the first step that you need to follow is to choose the suitable control volume. So this will be your control volume. Okay, the vein starting from the inlet until all the uh, it's not nice here. I will just redraw it again. Okay, dotted. So the control surface dotted line. Okay, this is the first step. So the second step, go back to the slide. Identify the inlets and the exit positions. So this is the inlet because you see here this is the arrow going into. So the fluid is going into the this one is vein. It's going on the vein. So this should be the inlet. And this should be the outlet. So normally we use number 1 as inlet, number 2 as outlet. So if you have more than one inlet, so 1, 2 inlet, and then 3 outlet, okay, and so on. Then identify all the external forces, including the pressure forces. Okay, so since this is a vein, okay, it's open, so there is no pressure force. Okay, if it's a pipe like this, if it's a pipe, you should have a pressure force. Okay? So as I mentioned just now in the previous slide, pressure force is acting normal to the surface and towards the control volume. So at the, let's say this is the inlet, this is the outlet. So for a pressure force, okay, this is a pipe. For a pressure force, it must be perpendicular to the inlet and outlet and towards the control volume, because this should be your control volume. Okay, so pressure force is pressure times area. Okay, so pressure times area. Okay, let's say this is pressure force 1, so pressure 1 A1, so pressure force 2 P2 A2. Okay, but this is for pipe lah. For vein, you don't have pressure force. And if let's say you want to include the shear force, if you have the value of the shear stress, then you can include lah. Okay? Shear force is shear stress times area, surface area. Okay? But normally it's ignored. Okay, except for the last topic later, I will show you if it needs to be included. Another one is there are two types of force just now. We have boundary force and then force across the force. Sorry. The force across the TV, which is the gravitational or magnetic force. Okay. So gravitational force, if let's say the pipe is, for example, a pipe bend. Okay. So you want to this is the inlet, this is the outlet. Okay, so pressure force, so velocity 2, this is 2, this is 1, so velocity 1. So you want to include the weight of the pipe bend. Okay, and also the weight of water inside the pipe vent. So there are two weights here. Okay. So if you want to include, then you can include. But in this example, the vein, I believe that the weight is also ignored. Okay. All right. So um the forces, the external forces, acting on the vein, and there's no external forces here because everything is ignored. Pressure force ignore, shear force is also ignore, magnetic force ignore, weight also ignore. Normally, in this example lah. Then the 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 horizontal and vertical component of the force exerted on the vein, or in other words, is the force exerted by the water on the vein, okay, can cause the vein to move lah. Okay, so therefore you need support. The vein needs to be supported. Okay, so this force, okay, I call it as reaction force. Okay, so reaction force can be assumed first. Okay, so we assume reaction force in x direction, reaction force in y direction. Okay, because the vein is has component. Has is directed 30 degree from the horizontal. So if you um, calculate the velocity here, there's component of x and y. Okay, so momentum has x and y also lah. Okay. Okay. So now you have identified all the external forces and also the force that is needed to support the vein lah. Okay. Alright. So ensure that the MCE is satisfied. So MCE stands for mass conservation equation. So make sure that the MCE is satisfied. So is this a steady flow? Okay. This is the flow on the vein. Okay. Meaning it's a steady flow. The velocity doesn't change with respect to time. Okay. So therefore, the mass, so since you have mass 1, mass 2, so the mass in is equal to mass out. Okay. So based on the MCE for a steady flow, okay, mass in equals to mass out. Okay. And then apply the FME in X and Y direction. Okay, so now you can apply the FME. So apply FME to X direction first. Okay, so since this is a steady flow, you go back to the equation. So this is the equation for a steady flow. And we assume uniform flow. If it's non-uniform, then you have to use this. Okay, so we assume uniform flow. So summation of Fx equals summation of m dot rate of momentum in x direction at the outlet minus inlet. So you write the equation first. The summation of force in x direction equals the summation of rate of momentum at x direction outlet minus inlet. Alright, so I always assume this as positive. I assume this direction to the right. Okay, so this is x, this is y, okay, in this question. So I assume x to the right is positive. So since we don't have pressure force, we don't have shear force, we don't have weight, we don't have magnetic force. The only force is the force exerted by the water on the vein. So therefore, you should have a support on the vein so that it won't move. Okay, so this force needed to support the vein is, I call it as reaction force. Okay, so this reaction force, I assume it to be to the right direction. Therefore, it's a positive here. Okay, so it's a positive. Okay, Rx. So there's no other force here. Okay, since everything is ignored. Okay, so in the X direction at the outlet. Okay, at the outlet I have. Okay, at the outlet I have. I have velocity. So the velocity is going to this direction, right? Okay, so I have component velocity in X direction with V2. So this should be cos 30. In Y direction, it's V2 sine 30. Okay, the angle is 30 here. So in the outlet, at the outlet, the mass, so since the mass flow rate is the same, I can simply use m dot only. Okay, because it's the same. So for both, the m dot is the same. Okay, you don't need to put 1 and 2 because you can reduce the unknown. And you can reduce the notation. Okay, use one notation only. Okay, so m dot times velocity in x direction at the outlet, which is v2 cos 30. So it's going to the right. So to the right, it's positive. So plus v2 cos 30. Okay, minus, so m dot should be the same. So at the inlet in the x direction, we only have this v1. Okay, so it's going to the right. Of course, it's a plus. All right. So therefore, Rx is equal to m dot. You can write once. Okay, so v2 cos 30 minus v1. So if, let's say, the question give you m dot or rho q, if the question give you q or velocity, you can actually use rho q. Okay, v2 cos 30 minus v1, because since this is an incompressible flow, rho is constant, so q1 equals to q2 equals to just one notation q. Or you can also use rho av. Okay, you use one of the area and one of the velocity. Let's say v1 a1 v1. Okay, so rho a1 v1. Okay, because this should be a1 v1, a2 v2, this a v, same. Okay, so v2 cos 30 minus v1. Okay, or a2 v2. Okay, can. All right. Okay, so you can get the answer lah. Okay, if you get a positive answer, meaning your assumption, it's in Newton. Okay, your assumption on the direction of the reaction force going to the right is correct. If you get a negative answer, meaning your assumption that the reaction force is going to the right is incorrect. So it's the other way, which is to the left lah. So you should state here, it's a negative if, okay, or if it's a negative answer in Newton, okay, that means it's going to the left. Okay, all right. So this is for x direction. If you apply to y direction, if you apply FME, okay, to y direction, so this will be replaced with y, m dot y. Okay, Remember that this m dot is capital M. Small m is for mass. This is momentum. Outlet minus inlet. So what do you, do you have a velocity component in the y direction at the outlet? Yes, you have v2 sine 30. Do you have it in at the inlet? No, because the inlet you only have x direction. So therefore the inlet this will be 0. Okay? And normally if the y direction is like this, I always assume positive upwards. Okay, so therefore positive upwards. Okay, so my assumption of Ry, a reaction force in the y direction is going up, it's a positive Ry. Okay, it's equal to m dot. So v velocity at the outlet in y direction is going down. So it's a negative v2 sine 30. Alright? So since it's a negative, your answer will be negative as well. Okay, your answer will be negative as well. That means, in Newton, that means the force, or reaction force acting on the vane, okay, must be going down. Okay, it must be going down. Okay, so your assumption on the direction is incorrect. Okay, but the answer should be correct. Okay, the value of magnitude. Okay, so this is how you answer this the application or the example of force and momentum equation. Okay, so we will continue with the real example in our online class, which is tomorrow. All right. So before I stop, so we have quite a few examples. Before I stop, I will just explain on the moment of momentum equation, okay, which is by using the previous momentum equation, you can also use it again, okay, to find the moment. So this is normally for force in all directions, something that is rotating, okay, like a water sprinkler, for example. So force is acting in all direction, right? Okay, and you will have to find moment or torque. Moment or torque. So torque is basically force times distance. So in this case, the distance, if I can show you, like this one. The force is acting in all directions. So normally we want to find the torque or moment. So to find the torque or moment, force times distance. So in this case, the distance is the radius. Alright. So if you go back to the momentum equation just now, the force and momentum equation or linear momentum equation, we only have m. Okay, so m. And this one we have force, F. Okay, so force times with distance, which is the radius, you get torque or moment. Okay, so you times with everything with radius. So this will be m times r, force times r, you get torque. M times r, m times r. Okay, so this equation is called as moment of momentum equation. Alright, it can be used for a rotating device lah. Okay, and if it's a steady flow, normally this control volume term will be 0. Okay, therefore the summation of torque is summation of moment, rate of moment at the outlet minus inlet. Okay, so this is an example, okay, of the use of moment of momentum, okay, water sprinkler. Okay, so that's the end of lecture 7. So I hope you guys can watch, can understand, And after watching this, if you have any question, we will discuss in the online class. So we will do the example in online class as well. So thank you.